When we send an email or stream a video, the data feels weightless. We call it the cloud, a term that suggests something ethereal and drifting high above the earth. But in reality, the internet is heavy. It is made of thousands of miles of undersea cables and massive, windowless buildings that hum with a constant, low-frequency vibration. These data centers are the physical heart of our digital lives, and they are facing a quiet crisis of physics. To keep our information moving, these facilities are consuming electricity at a scale that challenges our modern power grids. To understand why these buildings use so much energy, we have to look at the scale of a single bit. Every digital action involves moving electrons through silicon. In a modern processor, billions of tiny switches called transistors open and close billions of times per second. While we think of computers as logic machines, they are also heaters. Because silicon is not a perfect conductor, every time an electron moves through a transistor, it encounters resistance. This resistance turns electrical energy into thermal energy, a process known as joule heating. At the scale of a modern chip, this heat is intense. The energy density of a high-end server chip is actually quite startling. If you look at the surface of a top-tier processor, it generates more heat per square inch than the nozzle of a rocket engine. While a rocket engine only fires for a few minutes, a server chip must maintain the state for years. If a data center's cooling system were to fail for even a few seconds, the silicon would literally begin to melt into a useless puddle of glass and metal. We are essentially running millions of small, controlled fires just to process our search queries. This creates what engineers call the cooling tax. In many older data centers, for every watt of power used to actually compute data, another full watt is required to remove the resulting heat. This efficiency is measured by a metric called power usage effectiveness, or PUE. A perfect score is 1.0, meaning all energy goes to the servers. But fighting the laws of entropy is difficult. We have to move massive amounts of air and water through the building just to transport the heat away from the chips and out into the atmosphere, which requires enormous, power-hungry fans. Air is a poor conductor of heat, which is why the industry is moving toward liquid cooling. Imagine a network of pipes carrying chilled water or specialized coolant directly to the surface of the processors. This is far more efficient than fans, but it introduces a new set of engineering risks. Water and electricity are famously poor neighbors. These systems require complex plumbing that snakes through millions of dollars worth of equipment. Despite the risk, the sheer heat output of modern AI-focused chips is making liquid cooling a necessity rather than a luxury for the next generation of data cities. The scale of these facilities has grown from single rooms to entire industrial parks. A single large data center can consume as much electricity as a small city of 80,000 homes. In places like Northern Virginia or Dublin, Ireland, the demand for data center power is so high that it is straining the local electrical infrastructure. This isn't just about electricity, it's also about water. Many facilities use evaporative cooling, which can consume millions of gallons of water per day to keep the servers from overheating, placing a hidden strain on local environments. There is a fundamental limit in physics known as Landauer's principle. It states that erasing a single bit of information must release a minimum amount of heat into the environment. While we are still far from reaching that theoretical floor, we are running into the practical limits of how much heat we can pull out of a piece of silicon. As we cram more transistors into smaller spaces to make computers faster, the heat becomes more concentrated. We are no longer limited by how fast we can make a chip, but by how fast we can cool it down. To solve this, some companies are looking for natural heat sinks. This has led to the rise of Arctic data centers, built in places like Norway or Iceland. By using the naturally freezing outside air, these facilities can drastically reduce their cooling tax. Some engineers have even experimented with sinking entire data centers to the bottom of the ocean. The cold, deep water acts as an infinite heat sink, absorbing the warmth of the servers without the need for energy-intensive refrigeration. It is a radical attempt to use the Earth's geometry to balance our digital appetite. Ultimately, the energy problem of data centers is a reflection of our growing reliance on the digital world. Every high-resolution video, every cloud-stored photo, and every AI-generated response has a physical cost measured in joules. The internet is not a cloud. It is a sprawling, humming machine that lives in the physical world and obeys the uncompromising laws of thermodynamics. As we continue to move more of our lives into the digital realm, The challenge will be finding a way to keep the world's information moving without letting the machines melt under the weight of their own heat.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.